So I was saying that he's a professor at the University of Augsburg. He did his PhD in Munich in Erwin Frey's group. And as I was saying, I even wrote a comment of one of his papers during his PhD. Then he moved to Dresden, where he started to work on biological condensates. I also remember a very nice discussion that we had on that after one of your talks. And he is going to tell us about interplay between phase separation and molecular assembly.
Thank you very much for the kind introduction, and thank you very much for having me here. Indeed, also the talk by Jean-François was very helpful, kind of to also pitch the topic of my talk. I tried to resolve a few problems in the field by trying to be more precise on what is phase separation and what is not phase separation. And I think for that, of course, concepts from soft matter physics help a lot to help us, to tell us what is phase separation and what not. And this might be also part of the confusion and the critique in the field, that people are not agreed on the same terminology and the same wording, and also maybe are not expert in the other discipline. Yeah, it's very interdisciplinary, you should know. So I would like to tell you today about how you can think about the interplay between phase separation and molecular assembly. And let me introduce you from a slightly different angle to the topic. This is, of course, the cell is so exciting because it's spatially organized. And typical cells live somewhere here, between 10 and 100 micron, depending on cell type. And they show a spatial organization on all these length scales, down to 1 nanometers, that's typical of protein size. And spatial organization is, of course, nothing new, right? I mean, people, since the invention of the light microscope, they looked at cells and saw the organelles. And a good example of an organelle is, like, as shown here, like a mitochondria. So if you sketch a cell, and I hope soon in the future, when you open a cell biology textbook, you will find maybe a more beautiful one than this one. A sketch like this, that the cell is not just a bag full of organelles like the mitochondria, the cell nucleus, or whatever is inside the endoplasmatic reticulum. But also there are these rounded objects that are called biomolecular condensates. You know why they're round? Jean-François told you, I mean, there's a surface tension on long time scales. They behave like liquids, or many of those. And this exactly is another kind of important unit, how cells are spatially organized. And the reason why they had not been seen in the past is, of course, this is a very transient structure, because phase separation relies on diffusion, so things can form very quickly in seconds and minute time scales and also dissolve, right? So if you stain a cell, you should not expect that you have not killed phase separation, but presumably still the membrane-bound organelles still hang around and you can see them in the microscope. So it needed really the modern techniques, modern microscope, light sheet, for example, to really detect those and also to see the dynamics. So when you zoom in into those condensates, so the current picture is, as Jean-François also explained, is that you can see them as coexisting phases. And I'm doing as if they're just two coexisting phases, but this is completely the wrong picture. The cell is a bag composed of 10,000 different proteins and all kinds of components. So they're presumably not just two phases that coexist, okay, but just in terms of concepts. But there are also other units that are key to spatially organized stuff. And these are, and there are different words for that depending which community you grow up. I call them here molecular assemblies because they're just composed of molecules. So I'm thinking about monomers, dimers, trimers, all kinds of things. There's also, like in physics, we also often call them aggregates. You should not do that when you talk to biologists, of course, because they usually associate with that molecular assembly a disease or whatever, or even might associate an irreversible stuff that never dissolves, even on long time scales. So I don't want to use all those words. For me, this is just a molecular assembly composed of many molecules which can reversibly bind and unbind. So they can form and disassemble. And they, of course, live on a different length scale typically. So these assemblies usually are found in the order of 10 to 100 nanometers. And the units are, as usual, the proteins, RNA, DNA, and all kinds of stuff. And just also to make a very important point, the condensates themselves are not just two-component phase-separate objects. They are composed of extremely many proteins That's also having discrete names for those granules is a little bit misleading because actually there's a long vector of composition defining such a p granule. And if you change the condition like temperature, it's completely different as well. So it's the same with cell types maybe. Discrete names usually don't help to describe a continuous problem. But let us get step by step to the concepts, because in order to study the interplay, I have to tell you what I mean by phase separation, and let's do the first step, and then I make a more precise step using thermodynamics. So recently we have worked on this problem. Also, Jean-François has shown you some movies where you were increasing and decreasing the temperature. And the hypothesis why we did this was simply we want to probe how fast things form and dissolve. Can you really see this like an ouzo bottle where you increase and decrease the temperature? Yeah, and then they form and dissolve, and actually they do. But we were not just interested in that, we were also interested in kind of getting the local concentrations inside and outside. And this we did. And so we characterized the concentrations, the dilute branch, so to say, and the dense branch. And what you can see here, this is of course just a guide to the eye, this has the classical shape of a classical binary, simple phase diagram with an upper solution temperature here. We can't reach it because the cell dies above 32 degrees. But why did we do that? Because we wanted to understand how helpful are concepts from thermodynamics in order to understand phase separation in living cells. I'm not claiming that the cell is at thermal equilibrium, for sure not. Yeah? But I'm showing this indicates that, because we could also fit this with a classical polymer physics model, that concepts from local thermal equilibrium might be relevant to govern phase separation in living cells. So getting back to what is phase separation, sure, it comes with coexisting phases. We must be able to identify those. There needs to be a timescale for that. It's often said in the community that the proteins interact weakly by so-called multivalent interactions. Or just think about these polymers. They have multiple sticking units, okay? And if some or the other way, they can branch in that sense. And also on long timescale, these need to be liquids. Okay, be very careful if proteins, if condensates don't fuse, if proteins don't Ostwald ripen, it doesn't imply that they're solids. Okay, very important. Just like often there's a clearly limited timescale that you probe in an experiment. The cell divides. It's the elegans cell. From here you use the elegans. It divides after 20 minutes. So the question whether it's a liquid on 20 timescales is relevant, but whether if it doesn't recover and it doesn't after photobleach, for example, it's just important that then we can term it a solid, even though maybe on super long times it becomes a liquid. What is now different to molecular assemblies? I pick here two snapshots of two very important classes. One is membrane binding proteins, which are known to form oligomers. So we have a monomer unit that can stick to a surface, the membrane, and then it can oligomerize by forming dimers, trimers, etc. And this is very important to form all these units that connect cells. To mention just a few ones, the tight junction or the adherence junction, but there are many of those. Another important class pushed forward by people like Steve McKnight, etc., are these so-called amyloidal proteins that have a nice beta sheet by which they can stack on top of each other. So they can form perfect filaments that are rather stable and also rather irreversible, by the way, and can form these highly ordered structures. So here, I call those molecular assemblies. First of all, what is different to classical phase separation? Very simply said, you ask different questions, first of all. Here, you're interested in the coexisting between two phases that are spatially separated. Well, here you are interested in the distribution of sizes. So you're interested in what is the concentration to find a monomer, the concentration to find a dimer, etc. Often, but that's very misleading, in many cases, strong interactions are involved. Obviously, when you think about amyloids, very strong interactions are involved, yeah, in order to keep them together. However, as we have to be careful with these statements. It's not just the difference between weak and strong, because look at the work of Ludwig Leibler, for example. There are the vitramers that have really great covalent bonds, but they have a lot of kinetics. They're liquids, they can heal, right? So strong doesn't imply no dynamics, okay? What is more relevant is that I can distinguish the state I'm talking about. I can distinguish a monomer from a dimer and a trimer. And for that, the lifetime must be big enough in order to distinguish those, right? So the lifetimes of the bond, connecting, for example, here this amyloid or here this oligomer, need to be measurable, so in the order of minutes or seconds. Yeah? And then we can think about step by step whether on the timescale of interest something is irreversible or not. But I will mostly talk about reversible stuff today. You should not forget, these assemblies can do something else, and that makes this link to the question of structure in the field of biology, of course. They can form, of course, lots of ordered structures, translational order, like these fibril filaments, but also rotation order is possible. So before I go into thermodynamic concepts, let me ask the question of my talk. It will be a theory talk, so I will outline a few concepts and will show you how to describe molecular assembly and phase separation using a kinetic description. And so we'll combine exactly these two kind of pictures. We have coexistence between two different phases, often termed as dense and dilute. By the way, quick comment, dilute is not a good name in general. It's just historical. The dilute phase is not dilute, but it's called dilute phase. But we're already above the concentration to see density-driven phase transition. That's phase separation here. In addition, we have molecular assemblies. As I said, we're interested in the transition rates between monomer, dimers, trimers, and we have to go up to whatever biology tells us. It can be 100 mer, can be 1,000 mer, and at some point, well, what is 1,000 mer compared to this dense phase? We can connect exactly this question of what's the difference between a big, what Jean-François called aggregate, or a molecular assembly and a condensate. And I will ask these two questions, and I will convince you that you can't ask these questions independently in general. There might be special limits. And this is how phase separation affects molecular assembly and how molecular assembly affects phase separation. And the reason why you can't ask this independently because there's a mutual coupling between both. And this will bring us back to the role of the chemical potential in dense systems, because the chemical potential will govern the kinetics of both cases here. Just different ones. Here it will be the spatial gradient, and here will be the difference among the states. Okay, now let's get to the concepts. What is phase separation? What do we mean by phase separation? There's, of course, a well-defined definition when we go to thermal equilibrium, in that case, to phase equilibrium. So what is the condition that two phases coexist of different composition? Thermodynamics tells us this is actually they are at equilibrium if the temperatures, the pressures, and the chemical potentials among the phases here by these superscripts I and II are equal. Okay. Chemical potential. So I have here a subscript. What is the subscript here? It's not just a binary mixture. Oh, wow, yeah, I want to connect to the monomers and the dimers and the trimers to the aluminization problem. So what are my components? I have solvent. I always need solvent. Theories without solvent are very dangerous, just as the outlines, in particular when you think about chemical reactions. So there can be a lot of misleading statements when you ignore the solvent. But then we have monomers. So think about a protein, and that can also form a dimer and a trimer. So we have a lot of components, so M can be very, very big in general. Yeah? This is phase equilibrium. Let's define the assembly equilibrium. Quick comment before I do that. In general, we have to distinguish what is the dimension of the object that you're talking about. So, of course, we're in 3D, right? But is it a one-dimensional filament that grows? Is it a disk? Or is it a three-dimensional object that grows? Yeah? But here I suggest for a one-dimensional one, but we have this dimensional parameter here in the theory. I will show this to you. Well, so we have here very nicely these transition rates between the oligomers of different size. And what is the equilibrium condition? The equilibrium condition is simply the equivalence of the chemical potentials in each phase, 1 and 2 respectively, but between, in that case, the monomer with any oligomer of size I. True for all I, okay? So you appreciate the difference between these equilibrium conditions is here it's between space, and here it's between states, yeah? Between these, for example, okay? And that's a thorough definition. So like, okay, I know exactly now that this is difference. There's fundamental difference when I ask thermodynamics, and now I can ask, okay, when I do now kinetics and develop a kinetic theory, what do I get from the interplay? Yeah? Okay, but I have to. I assume that not everybody is used to this term chemical potential, and I would say this is really an abstract quantity. I mean, when I started thinking about the field the first time, it gave me a hard time to explain this to biologists. So let's start step by step. What's the chemical potential I'm looking at here? It will be the chemical potential of a monomer or in an assembly of size I. Okay, fine. So it could also ask for the chemical potential of the assembly itself, but I ask for a monomer being an assembly of size I. Good, that's a detail. How can I think about it? What is the definition of the chemical potential? The chemical potential is you take it and you put it into environment with some interaction, including all its surroundings. So the chemical potential is not just the bare energy to create the molecule, it is the energy to put in a respective environment with all its respective interactions, like a phase. Mathematically, it comes with this, not very difficult definition, but it's just the derivative for homogeneous systems with respect to concentration or volume fraction of the free energy density. And I will, throughout my entire talk, I will talk about volume fractions of an assembly of size I. You can also read this as mass fraction, or if you like, as concentration. It's completely equivalent, but volume fraction is beautiful because everything adds up to 1. It's just a nice quantity. And it's very easy how to use in compressibility. But after introducing these fields, how I characterize my system, I have to introduce this quantity, the conserved quantity of the problem. So if my box is closed, so I'm not feeding anything, if I have just transition between monomers, dimers, trimers until m-mers, the total mass of all the oligomers is conserved. Okay? So I have a conserved quantity, and I outlined this here because later on in thermodynamics we will revisit this quantity a few times. What's the free energy? I could, of course, cook up a lot of free energies, but there's, of course, a systematic way of doing that. I mean, you can derive this coming from the partition function. You can also read this as an expansion in terms of higher order Varier coefficients. I just go up to second order. How does it look like? What are the terms of this free energy? First of all, I have a mixing entropy. So I have one from the solvent and one from all the components. For the experts in the room, it took me some time to also find it in some old book from Dijon. We recalculated, but then I realized, okay, this had already been done. There's often, in literature, this is often neglected. Yeah? So this is what is I? I is the size, the number of monomers in an aggregate. And there's a reason for that, because people usually apply to phase separation there, this factor doesn't matter, but now apply to assembly, so that's very important. So if you carefully calculate from the partition function, you actually recover that in the mixing entropy. What are other contributions? I have, of course, the internal free energy. So where omega I is exactly the bare energy to create the molecule, just like what does it cost to create it. And then I have interactions, and just separate into two parts, one between solvent and the oligomer, and among the oligomers. And here I just go up to second order. My results today will not change much if I go to a cubic term or even higher orders. So it's like a mean field kind of free energy, but higher orders will not change, at least not the qualitative messages of my talk. Okay. But before we get started, I have to talk about size scalings and the interaction parameters. Because what are the parameters that I have? First, we have this chi interaction parameter that told me about how much energy do I get when I bring two molecules together. And for example, here, when I have chi 2, 3, what does that mean? I bring a dimer together with a trimer. Yeah? And then chi 2, 3 characterizes somehow the associated energy with that bond. Yeah? In general, when you do it carefully and think about it, chi can depend on size. Yeah? And this has to do, and I will not go into this today, but when you think about proteins, they're complex. So at least the picture is, they have certain domains that phase separate and certain domains that oligomerize. I mean, this is, of course, not true. Yeah? That depends from case to case. But it could be, upon forming an oligomer, that the domain that really made you phase separate from the solvent gets screened away. That can easily happen. But it can also be that you have really separate domains, and one is relevant for phase separation, the other one is relevant for oligomerization. So this picture actually will also allow you to derive systematically a size dependent for this one, but just for the experts, I mean, we will not do this. I assume it's just a constant, so as in a classical Fourier-Huggins lattice model. However, when I think about the internal free energy, I can't deal with a size-independent constant. And why? Think about a simple linear aggregate. I mean, each bond contributes an energy, let's say some contribution delta omega. I can split this up into an enthalpic and an entropic contribution. And then when I derive that, the internal free energy of a component that is composed of I monomers need to depend on the number of monomers that I have, because it will, in a linear fiber, it will scale with the number of bonds. So you will exactly pick up this I factor, and if you do it carefully, you will also, for one-dimensional stuff, D is just 1. But of course, for higher dimensions, you will pick up here a simple scaling factor. Yeah? But that's important, because that's something I can't neglect. Here, I can find some, oh, I'm sorry, this is like, Google wants to talk to me. Pattern. Obvious, yeah. This kicks me back, so where did we stop? We had been here. So complicated? Come on. So, doesn't react. Okay. I'm sorry. I thought I switched off all updates. Okay, at least then you pick up this length scaling here. I told you I will show you kinetic theory. So kinetic theory for these systems, okay, what is the system again? We have a solvent, we have monomers, dimers, trimers, a lot of high-ordered oligomers. In principle, when you have this, when you have kind of these transitions going on and phase separation, we have to think about a spatial temperate kinetic problem. And this is super hard now because we have a lot of components. So this will bring you and connect you with this classical literature of nonlinear partial differential equation, often called Canhila type of equation, but also with a reaction term. And this I could do, but I can't show you results now for oligomers up to a size of 100. And you could imagine why, because the associated phase diagram space has 100 dimensions. However, we can reduce this a little bit into a regime by using a timescale separation that is mostly relevant for this problem. And this is when we assume that diffusion, so spatial diffusion between the phases, is fast compared to the assembly process. So just think about, and this comes with a length scale usually. Yeah? I'm just assuming indirectly that the condensate size and the outside is not, or at least the distance to the next condensate is in the order, let's say, of this length scale. And if you do that, if you plug in real numbers, diffusivities of 10 to 100 micrometers squared per second, and typical assembly timescales, I introduced this 1 over a minute, for example, then you get length scales in order of 10 to 100 micrometers. So there are no spatial gradients expected on that length scale. The advantage is, when you do that, you can systematically derive, by the way, true for any chemical reaction. I mean, it's not just limited to assembly processes. You can get, instead of PDEs, you get simple ODEs. So the time evolution of the one fraction of component I in each of the phases, and you get here this right-hand side. So what is the right-hand side? So the first one is simply an exchange current between the phases. The second one is the assembly rate. Yeah, that depends on the component and the respective phases. And in addition, you also pick up, because you're not dilute, we're not doing a dilute aggregation or agglomeration theory, you also pick up a volume change, because as the reaction runs, as you exchange material between the inside and outside, you are moving in some way through the phase diagram, yeah? And the volume can in general change. But this assumption kind of creates a crazy constraint, is that your kinetics is such that the entire system always runs along the binodal. It's a very high-dimensional binodal, so the system always decomposes fast into the phases, and then you get a flow on the binodal manifold. That's how you can picture it. If you want to read more about that, we worked it out systematically, and it has been recently published. How to construct the assembly rate? It's just, you just count. You just count, classical, like as you do in a master equation, the events of, let's say you have an assembly of size I, what is the number of events that transition from here to here and back. Yeah? So you can write down such a transition rates. But what I would like to stress here, the transition rate between assembly of size I and I plus 1 looks like this, where the rate moving forward or backward is the same. That ensures that I relax actually to thermal equilibrium. So I have just one time scale to relax for each transition. And when this bracket here in the exponential vanishes, so it's 0, exponential of the 0 gives a 1, 1 minus 1 is 0, I'm at thermal equilibrium. Yeah? This is exactly, so these are exactly my previous equilibrium states. If you plug this in the previous condition, you see that this one is 0 for each I at assembly equilibrium. So I'm not in a hidden way introducing here some ghost that maintains the system out of equilibrium. I could do that, but then I have to say it. I have to say that I have a fuel reservoir that drives some transition, that has some phosphatase, some kinase that is maintained from the outside, that maintains it out of equilibrium. I can show results about that, but I don't have it here in this talk. So if you're aware of the classical aggregation theory, going back to the classic paper of Smolonkovsky, you could honestly say, Nice. This just sounds like a non-dilute aggregation theory. Yeah? And my answer to this is absolutely true. Yeah? I don't want to hide. Yes, indeed. The only thing what we do is we look at assembly. I just call it non-molecular assembly instead of aggregation at high concentrations, normal dilute. But that exactly allows me now also to phase separate and discuss these phenomena. But there's a problem. There's a reason why people have not done that. I assume, I hope not, they have not done that. Even though I've neglected, I did this harsh assumption of neglecting any spatial degree of the problem by separating the timescales of exchange between the phases and the formation of the assemblies. I have many components. I have the solvent and dimers, trimers, etc., and MS. So I have a phase space, or actually better say like a phase diagram space that has m+1 dimensions. Hold on. Okay, I assume incompressibility because I'm in solvent and water, so I have just m. But m is big. But with this separation of timescale that the exchange is fast, I know that at each time point the system is at phase equilibrium. And that allows me to do a very beautiful construction, what I now refer to, I can create a chemical trajectory of the average concentrations. So you can write on the average concentration like a vector here of all the components. These are not they're different in each of the phases, but I just need to know the averages. And then, just here illustrated in 3D, I can draw something like this chemical space. And then the average is creating a trajectory here, yeah, that I can compute now using this kinetic theory. And at each time point, it decomposes into the two phases, okay? So if you give me the average at a certain time point, I have to do a Maxwell construction in that high-dimensional space, okay? That is doable. And then I know exactly with the ODE equations how to update it to the next time point, and then I redo it, and I do again a Maxwell construction. And that actually works because if you do it incrementally, you can even run here easily in 500-dimensional spaces. That's no problem. You know? So this is about the concepts. If you have more questions about that, I'm happy to tell you, but then this gets very technical, how to deal with the numerics in this high-dimensional space. But I would like to show you some results that actually I find very exciting because I guess this could help kind of to clarify some observations in biological condensates. Let's start with talking about the kinetics. So when I show you some kinetic trace, I have to tell you how I initialize the system, right? So what is my initial condition? I mean, when I think about assembly, it might be useful to just start with the monomers, because then let's say, okay, let's let them oligomerize and maybe then they phase separate. Well, if it's phase separated, if the monomers can phase separate, then we have these two coexisting phases that goes fast. They're all full of oligomers. Let's say this phase is a little bit up concentrated in oligomers. You see this here. That's the dense phase. That's the oligomer concentration. Here, these are just the oligomers. All the other monomers, I'm sorry, I should have said monomers. These are the monomers. And all higher order oligomers are all 0. And that's the dilute phase, just low concentrated. So let it run. Let it run as a function of time. What you see, interesting. So the dilute phase was immediately losing some monomers and creating this little distribution here, very weakly decaying. And the dense phase, interesting. Still a little bit kinetics around, actually create this extra peak here, which is normal at the monomer peak, which you've never seen when you do classical dilute aggregation theory. You zoom in, do a log-lin plot, you can verify the dilute phase in that case is dilute enough not to ruin your exponential decay, even though it doesn't have to be exponential, but it has a nice exponential tail here. While the dense phase, as you've seen here, this corresponds to that one, has a nice maximum. Yeah? At some oligomer that is not the monomer. So oligomers are experimentally rare, while oligomers get more abundant. So it's no more the monomer that is the most likely species in my problem. That's, of course, because it's not dilute. You can now look at the same system again and monitor the total volume fraction inside the phase. I should maybe go back, otherwise I spoil my message. I can now show you the same kinetics again, but now I look at two different quantities. I look at the total volume fraction outside, and inside. But I also plot here the volume of the droplet, because as I told you, it could change in principle because we know more dilute. And indeed, this is what happens. So the dense phase gets denser, while the dilute phase gets more dilute as a function of time. And at the same time, the volume of the droplets, in that case, increase in time. So they swell. polymer language. So why is that? Let me first explain the left-hand graph. The left-hand graph is actually generic. That's beautiful. So I don't have to tell you how I put all the interaction parameters. That always happens. And why does it happen? Because remember, we have a mixing entropy here in the problem. Yeah? The mixing entropy actually gets diminished as things get longer or bigger. So as you go from monomers to high-order oligomers. That is the reason why the dense phase gets denser and the dilute phase gets more dilute. Well, but when does now a volume increase? I can tell you, no, that's not generic. Well, the volume of the droplet can actually increase or decrease. I just show you one example where it increases, and the reason is simply the densification is more pronounced, so it outcompetes the dilution of the dilute phase. And so the volume can actually grow, but also shrink. And this depends essentially on how the molecules interact. That's a rough statement I can give you now. So now for that we have to go into details, how to put chi, is there size dependence or not. But upon going through different proteins, you can get either growth or shrinkage. But this is always generic. And this is actually supported because there had been a recent nice paper by Louis Jarvett, also from the Dresden people, where they actually observed, Jean-François already mentioned the Fus protein is a very important protein to study in the field, that they can shrink. So they get more condensed. You see, like this is at least consistent. But one has to now look into details and compare with experiments how to describe interaction among proteins. Now let's introduce temperature, because temperature is kind of the classics control parameter in phase separation. And in order to do that, I have to tell you where temperature pops up. Actually, it's a little bit not satisfying because everything depends on temperature in thermodynamics. All these response functions have a carrier temperature dependence. But the key one is the internal free energy. And that's well established how to put it. We have this enthalpic and this entropic contribution. And then we can investigate how the system changes in temperature. For the experts, I put the interaction parameter temperature independent. So what do we observe? We see at equilibrium that we have two phases with different size distributions, where the dense phase has much bigger oligomers compared to the dilute phase. So this you have already indirectly seen. Let's connect this now back to a phase diagram picture, because that's obviously very powerful, because we at each time point we are at phase equilibrium. So we can do something that maybe doesn't feel, from the first step, maybe feel very good, because you want to also rationalize maybe even a kinetics in a phase diagram, but we are at each time point we are at phase equilibrium. So let's fix a temperature and fix a total volume fraction here. The system decomposes into, according to the classical picture, into two liquid phases. One is less dense in terms of total concentration, one is more dense. Well, it looks like that I'm showing you a super boring old diagram with an upper critical solution temperature and just with, there's a binary. I mean, I talked about so many components. Well, no, I'm showing you really a multi-component phase diagram, but there's only one conserved variable. So remember, we had, with incomplexity, we have had in the end m components, m independent components, but we had also m-1 assembly equilibrium conditions, which has left us with 1 degree of freedom in the end, in my phase diagram, and that is exactly, of course, my conserved variable. Yeah? So this diagram comes from essentially integrating out, or solving in this m-dimensional space all those conditions and then getting this diagram. Okay? But you can now visualize it, that's the beauty. Yeah? So let's now change temperature. Same system. So we decrease temperature now. As you do that, you can actually find another transition. And this transition is now that the system forms, there are two coexisting phases. One is a liquid, and the other one is a gel. What do you mean by a gel? So if I look into the size distribution of this dilute branch here, I find a strongly decaying, if you plot log ln, it will be exponentially decaying, liquid branch here of the size distribution. But there's in a thermodynamic phase diagram, everything's infinitely big in that sense, I have a peak at infinity. That is my gel. What does that mean? just means that this phase is just one cluster, okay, the dense phase, just one connected cluster. Yeah? Well, you don't have to speak so complicated. In a finite system, this simply looks like this. Everything is connected, and I can replace this infinity here by the total volume divided by the molecular volume of the monomers. Yeah? So the dense phase can become a gel. And that exactly connects very beautiful to the classical literature of gelation in the field of aggregation. Yeah? But now we have coexistence between a gel and a liquid. And this had been suggested, by many works, but by the way, my references are not representative at all. I mean, I think per week I get 30 new papers on my Google search bot, so I can't read them all, so I cannot be complete. It's strongly biased, so I'm very sorry that not to give you an acceptable overview of all the references, because there's so many papers published in that field at the very moment. So that's why sometimes I write here EG. And this is a beautiful paper. Have a look at that one. They already suggested this picture from several biological observations. And of course, hooked up with this, even though I sketch it here like spherical symmetric, which can be, of course, the case, but it doesn't have to be, because on the timescale of interest of the formation, the system might not have enough time to relax it back to a spherical shape because of surface tension. Okay, let's switch gears a bit and look at the regime that is seemingly boring from the perspective. I present you now a non-dilute aggregation theory. Let's get back to the dilute condition and see what is altered in that regime. Let's look below saturation. Just remind you, what is saturation concentration? The saturation concentration is the concentration above which you find condensates. And as I've shown you also, inside each of the phases, there are different size distributions, right? So the control parameter is also, thermodynamic one is the total mass concentration. Let's decrease this now. Let's decrease it to really super tiny values. Okay, then it gets boring. We just get such a thing, right? Just monomers. No phase separation. The monomers even can't see themselves, so even can form dimers. So dimers are ultra rare. So if I look at a size distribution, it's strongly decaying, so it decays exponentially with a characteristic length of the size of the monomers, so 1. If you increase now again the total concentration, you go through another threshold. It's called the assembly threshold. I call it threshold because it's not a phase transition, right? But something interesting happens now. When you carefully account for the interaction among the components, even though they remain homogeneous. So, for example, here, these are just like a different size distributions for increasing phi tot. Yeah? You get bigger and bigger aggregates, but you see like also here there's a clear maximum each, right? So you form oligomers already below saturation, okay? And the monomer is not the most abundant one. So below saturation, it's the expectation that you find a strongly exponentially decaying distribution is not correct. Yeah? I'm not saying that below saturation, all proteins hang around in a dimer or trimer state. I mean, for that, you must be able to form, of course, oligomers, right? But if you can, you would expect such a picture below saturation. You see a broad distribution of finding very easily a 10-mer or a 5-mer. This has been actually seen. There has been huge debate in the field, to be honest, because measurements bridging from here to here are hard, right? You have to be able to see molecule sizes up to phase-separated stuff. But you can look up the reference. So last slide. We can now go back to our phase diagram picture. And I can depict now these three systems, very low concentration of phi tot, increasing ones, phase-separated, here in the phase diagram. Well, here we are very low, right? This is this one. Then we increase it step by step. Then we go through the binodal and then phase-separate, right? But I can also compare it to a system with only monomers. I can just say, like, I just gave you the monomers at t equal to 0 anyways, and you form the oligomers, etc. This is a thermal equilibrium statement here. But I can also say, like, yeah, I give you just the monomers, and I block the ability to form oligomers. Then the binodal would look like this, of the same system. I mean, look at this rescale temperature is just dramatically different. Huh? So if I had sit somewhere here, the actual system that can form oligomers can easily phase separate, while giving you just the oligomers, it never can. Yeah? So we see that the ability to form assemblies can crucially affect phase separation propensity. And the expert might argue, okay, fine, this is somehow easy because somehow you tweaked here in the order of a few kbt the interactions, they enter an exponential, so you expect, of course, a huge change. Yeah, but that's what biology is doing, right? And this suggests an interesting picture, and I can't tell you whether this is true, but I would like to communicate it to discuss about it. And this is whether molecular assemblies can act as a nucleator for phase separation. Yeah? So let's go back to this. I just give you the monomers, but now allow oligomerization, but I give you this now kinetically at t equal to 0, and let the system do its job. What does it do first? It can't phase separate here, so I put the system here. Yeah? But, oh, sorry, I mixed up the colors. Yeah, it was today in the train, I'm sorry. So the system sits here at a fixed temperature and a certain total concentration. So here, because I have just monomers, the system can't phase separate. But what it can do, as a function of time, it can build step-by-step oligomers. So now I move up. Yeah, you see like here, this orange point detaches step by step. I form more and more oligomers. And at some point, I go across this, should be another color, it's red. Maybe you can see it because of beamer. You cross the phase separation threshold and you phase separate. Yeah? So meaning the system first oligomerizes and then phase separates later on. Yeah? So I think it might be a helpful picture because many proteins can oligomerize, but that they phase separate, this is more or less established now. I think they're all more or less phase separate. Yeah? Good. So I showed you now that the slow formation of oligomers can actually trigger the formation of coexisting phases. So let me quickly summarize. I showed you that when you combine or study the interplay between phase separation and oligomerization, that in each of the phases you can find significantly different size distributions, that the droplet can even gelate, linking up all this nice literature on amyloids and ALS, etc. And also that by increasing the total concentration, you get in the end that the monomers are no more the most abundant components, and that actually molecular assembly can significantly affect and change your saturation concentration. Now I'm at the end of my talk. Big thanks goes, of course, because I still feel like I'm still with one foot in Dresden. Left Dresden a year ago. Worked a lot with Frank. And also this paper speaks also with Thomas Michaels. And the superstar here in this project, what I showed you today, is clearly Giacomo Bartolucci. And I would like to thank all my collaborators, particularly those guys, and I would like to share also Klaus Seidel, who's now really trying to experimentally, because I can show you some theory, but the true challenge is to conduct experiments to link molecular assemblies composed of a few molecule sizes up to phase separation. And he's a spectroscopist, and now pushing forward new methods to close this gap. I'm at the end of my talk. Thank you very much, and I'm happy to have questions.